Speaker Professor Viswanath from Math Science, Fellow of Indian Academy of Science. He will be talking actually wonderful world of symmetric polynomial. We love symmetry, but I don't know whether that symmetry is related with a symmetric polynomial or not. But he is truly going to show us the beauty of symmetric world of symmetric polynomial.
So I'm going to talk about something that Raghavan and I worked on with one of our recent students, Mrigendra, who is now at the University of Delhi. So title is Refinements of Littlewood Richardson Coefficients and Saturation. So my goal is largely to explain the terms of the title. I'll just say a little bit about proofs. Okay, so symmetric polynomials. So what are they? So firstly, they are polynomials in n variables, x1, x2, xn, and the property we require is that if you permute the variables any which way, the polynomial should remain unchanged. So here are some examples. You take the sum of all the variables, that's of course invariant when you permute them. Here's another, you take the sum of the squares of the first, this is an example, 3 variables, you take the sum of the squares, and then 5 times the sum of terms taken 2 at a time. Okay, so sums of products taken 2 at a time. Here's another one, so this is in n variables, this is a familiar Vandermonde determinant or product, and you have to square it in order to make it symmetric. So this is a square of the Vandermonde. And this theory actually goes back a very, very long way. So all the way back to at least the 16th century, coming from the theory of equations. So you sort of have an equation, so the sort of stuff that we try to do in high school algebra. You're given an equation, you try to write the first coefficient is the sum of the roots, the second is the sum of the roots taken 2 at a time and so on. So that's sort of the genesis of the whole thing. So the names here are Cardano, who gave this famous formula for solving a cubic, Vieta, Girard, Newton, and so on. Okay, so now what I want to describe are some ways of manufacturing symmetric polynomials. Okay, so I'll talk about 3 different ways. So the first one is what physicists would probably call bosonic symmetrization, which is, well, it's just fancy name for the following. Just take a monomial. So here x1, x2, x3 raised to the power 7, 7, and 1. So I'm doing this in 3 variables. You keep the exponents fixed and you sort of move the variables around. You will get a bunch of different monomials. You add them all up. So it's sort of symmetric by construction. So this is what we would call the monomial symmetric function associated to the exponent list 7, 7, 1. And as you vary this list of exponents, you take all the other possible exponents, you will get different monomial symmetric functions, and they'll form a basis for the space of all symmetric polynomials in 3 variables. Okay, now here's the second way of doing this, which again, to take a physics term, would be called fermionic symmetrization. So it's the following. You start with the same, so here's the example with the same starting monomial 7, 7, 1, 3 variables. Now here you need a sort of first step, you sort of make the exponents distinct in a very precise way. You sort of add 0, 1 and 2 to these exponents sort of starting from the right. Okay? So if they were not distinct to begin with, they are certainly going to be distinct at the end of this. And then you you sort of do what we did earlier, which is to form all possible monomials obtained by permuting the variables, but now you take them with a sign. Okay, so it's, for example, here x1 to the 9, x2 to the 8, x3 to the 1, but the second monomial here is obtained by sort of switching 1 and 2. So that's like an odd permutation. Okay, so that gives you a sign of -1, and then the next guy is a sign +1, -1, and so on. And if you sort of look at it, what we are really doing is just, in fancy terms, writing down or evaluating this determinant, okay, which is x1, x2, x3 along the 3 rows with 1, 9, and 8 as the exponents. And this is sort of the familiar Vandermonde determinant or some mild variant thereof. So the Vandermonde determinant, if you remember, is sort of you put 1 x1, x1 square, 1 x2, x2 square, 1 x3, x3 square, and evaluate the determinant of the same thing, but with slightly different powers. So instead of x1 to the 0, 1 and 2, you just put the powers 9, 8 and 1. Okay, so I'm just calling this the Vandermonde or the generalized Vandermonde determinant 981, and the familiar Vandermonde is just product xi minus xj is just corresponds to 210. Okay, so I haven't yet done any symmetrization here. So when you sort of construct such signed sums, what you are actually making are antisymmetric objects. If you permute the variables, you will get the same thing, but up to a sign. Now, what we do to make this symmetric is the following. You look at the Vandermonde 981, and then you divide it by the sort of the basic Vandermonde 210. Okay, and doing this actually gives you, what we are doing is taking a quotient of two antisymmetric objects, and I mean fermionic in the sense of you construct these antisymmetric things, but fermionic symmetrization in the following sense, your final output is symmetric by sort of dividing by the basic Vandermonde determinant. And this guy is what's called the Schur polynomial, and again they form a basis for the space of symmetric polynomials, in this example in 3 variables, as you let this lambda vary over all possibilities. So what are the possibilities? You let lambda vary over vectors of length 3 with integer components, positive integer components, which are sort of weakly decreasing. So 7, 7, 1, for example. Okay, and these guys actually appear all over the place. They're ubiquitous in mathematics, certainly. They appear in representation theory, geometry, probability, combinatorics, tons of other areas, but they also appear in many other areas. So I've just listed a couple of things in physics. So they occur in what are called 6 vertex models. They occur in the fractional quantum Hall effect, sort of certain generalizations of these. They occur in computer science, in geometric complexity theory, for instance. Okay, but for the purposes of today's talk, I am most interested in this third way of manufacturing symmetric polynomials. Okay, so these are what I call manufacturing symmetric polynomials via the third method, and this is via some divided difference operators. Okay, these are some special operators which are, well, first discovered by de Maizière. So they are the de Maizière operators. So here are the operators. The formulas are right there up on the slide. So what it does is, given a polynomial f as input, the first operator T1 will sort of act on the first 2 variables alone. So observe, it's x1 times f, x1, x2, x3 minus x2 times f with x2 and x1 swapped. It sort of swaps the 2 variables and then multiplies things by x1 and x2 and so on, and divides by x1 minus x2. Now T2 likewise operates on the last 2 variables, on x2 and x3. Okay, now these operators have the following properties, that they don't quite produce symmetric answers. The final output is not a symmetric polynomial. T1 of f, however, has some partial symmetry. It's symmetric under the swap of x1 with x2. T2 of f is symmetric under the swap x2, x3. Okay, and here's the interesting bit. However, if you apply them in this, in the following way, you apply T1 followed by T2 followed by T1, it turns out to give you the same answer as T2, T1, T2, and this guy is, the final answer is symmetric. Okay, it's a symmetric polynomial, and in fact, it coincides with the, what we call the fermionic symmetrization. Okay, so here's the same thing in a picture. So what we are really doing here is starting with sort of a seed. So we start with x1 square, x2, and what I said in the second way of producing symmetric polynomials, if you take this guy and you perform, I'm assuming I'm talking about 3 variables here. So I take this basic guy as my starting monomial, I do fermionic symmetrization to it, what I'll get will be the Schur polynomial, right, the one on the top. But now this third method via divided difference operators allows you to get to from the bottom to the top through a bunch of intermediate steps. Okay, so you apply T1 and T2, these 2 operators. So thereby producing, there are sort of these 4 intermediaries. Okay, so there are 6 polynomials in all, the basic seed being the starting monomial and the apex of this being the Schur polynomial. So I'm just going to complete this into a hexagon there. The 2 green arrows don't mean anything, green lines at this point. Okay, and we think of this therefore, so what's the point of doing this in this third way? What it gives you is sort of a progressive non-symmetric approximations to the Schur. Okay, so the fermionic symmetrization would just take this as input and sort of spit that out as output. But this sort of process of using these operators gives you a bunch of intermediate non-symmetric polynomials, have some partial symmetry, but they're sort of some nice approximations to the final answer, and they're progressive in the following sense. As you sort of move up the arrows, you sort of get more and more terms. You pick up more and more terms that will exist in the final answer. Okay, so you start with just one term, you get more and more till you finally reach the intended answer. Okay, and these 6 guys are all called de Maizière characters. They are obtained by applying the de Maizière operators to the starting seed monomial. Okay, so here's another important thing. We think of these 6 polynomials. So let me go back, sorry, should go back one slide. So these 6 polynomials or this hexagon, we should really think of as in some sense being like, you could do the same operators, the red and the blue operators as follows. You could, instead of operating on polynomials, on say the starting polynomial, just imagine you have the permutation 1, 2, 3, just the numbers listed in their usual order, and instead of T1, you perform the operation which swaps the first 2 coordinates. So here 1, 2, 3 under the red arrow becomes 2, 1, 3. Okay, and the blue arrow swaps the last 2 coordinates, a little bit like what T1 and T2 did to the polynomials themselves. So sort of here are 2 parallel pictures. So this is the 6 de Maizière characters. These are the 6 permutations of 1, 2, 3. Okay, and in fact they are in 1-to-1 correspondence. So here's what I'm calling sigma is a given permutation, and the corresponding de Maizière character that you get is what we'll call dem sigma of the starting monomial. Okay, so to summarize, we want to study the Schur polynomials, but we can actually also construct a bunch of successive approximations to them, which are in 1-to-1 correspondence with permutations. Okay, so the final problem, what I call saturation, concerns what you get when you multiply Schur polynomials together. Okay, so this is the multiplication of Schur polynomials. So I can take the product of 2 Schur polynomials. So here's an example. I have S210 times S110, and it turns out that the answer can be rewritten again as a sum of Schur polynomials. Okay, it turns out to be in this case 1 times this plus 1 times that plus 1 times this. Here's another one. And these numbers in red, the coefficients which tell you how many times a given Schur appears. That is, those are sort of like structure constants. So you multiply these 2 basis elements together, you write the answer back in terms of the basis elements, and the coefficients that you so obtain are what you would call the structure constants with respect to this basis, and these numbers, the ones in red, are what are called the Littlewood Richardson coefficients. Okay, so that was one of the terms in my title. So they are what you get by multiplying Schur polynomials together. Now let's do this de Maizière style. So you want to multiply Schur polynomials, but you want to sort of also do it in a way where you can get some approximations to the final answer. I don't just want S lambda into S mu, I also want to produce some successive approximations to this final answer. Okay, so that's sort of the philosophy here. Now how do you do this? Well, you use the de Maizière operators, because that's what will give you the approximations. So how do we do this? So here's the answer. The same hexagon, you run the same machine, T1, T2, T1, but you start with this as the seed. You start with x to the lambda times S mu of x. And then you run this machine, what you will get sort of at the top, the apex, is the product. If you did this with just this monomial x lambda alone, what you get at the top is just S lambda. Okay, but now we want the product on the top, so we sort of have to start with this particular guy on the bottom. Okay, so that's the main starting observation, and so now here's our approach towards constructing some sort of approximations to the product, which is you say, okay, I don't want to start with, so let me go back one slide. So x to the lambda S mu is what I had. Now I want to start with x to the lambda dem mu with respect to sigma, some approximation. I want to replace the S mu in the seed by one of the de Maizière characters corresponding to this. And then when I run this, I will sort of get something on top, okay, which is some approximation to the product of Schur functions or Schur polynomials. And that guy there has a name, it's called the Constant-Kumar character, which is essentially what you get by starting with this seed and then running the de Maizière machine till you get to the apex of the hexagon. Okay, and they turn out to give you progressive approximations to the product S lambda S mu as you choose different sigmas, as you choose sigmas which are varies over the 6 possible permutations. What I will get are really 6 different approximations to the product of 2 Schur functions. Okay, now, so what does that allow us to do? The product of Schur functions, when expressed back in terms of Schur functions, give you Littlewood Richardson coefficients. Now we sort of have the same thing but with the Costa and Kumar character. We replace the product of sure functions by any one of the 6 approximations, k, lambda, sigma, mu, and express this guy. This is again a symmetric polynomial. Write this back in terms of the sures, and what you will get will be some other coefficients which are going to be typically smaller than these numbers. So this is for the full product. This is for some partial approximation, some smaller thing than the whole. So these numbers will all be smaller than the final Littlewood Richardson coefficient. And when sigma is 3, 2, 1, when sigma is sort of the permutation corresponding to the apex of the hexagon, you get back the actual number. This is the full number C lambda mu. Okay, but in some sense we have 6 different refinements of that one single number of the Littlewood Richardson. So let me show you. Okay, here's another important thing. This guy increases as you move up the hexagon. So it's an interesting sort of way of taking that one number that you wanted, the Littlewood Richardson coefficient, and sort of distributing it along the vertices of a hexagon. So let me show you how the picture looks. If you didn't do hexagon, is a little bit more interesting. So now I'm going to length 4. So there are, hexagon is like 6 permutations of the number 1, 2, 3. Now I have 24 permutations of the numbers 1, 2, 3, 4. So there are actually 24 points in this figure. Okay, and what this is again the same thing, C lambda mu nu of sigma, as sigma varies over the 24 permutations of 1, 2, 3 and 4. Okay, and what you see on the top is 35, that's the full Littlewood Richardson coefficient. What you get when you take lambda, mu and nu to be these vectors of length 4, that's 35 is the full Littlewood Richardson coefficient, but these are all the refinements. There are sort of 24 refinements of that LR coefficient. And you can see that as you sort of go up these lines, these coefficients will all increase. Thank you. I will finish. Okay, and here's the saturation. So refinement appeared in the title as well. So I've told you what refinement I'm talking about, and now let me tell you what saturation means. So saturation is the following statement. It says that it's a statement really about non-vanishing for Littlewood Richardson coefficients. It says, so you fix some lambda mu nu, you fix some number n positive, say for example n is 10, and if C n lambda n mu n nu, okay, you take the Littlewood Richardson coefficient where you scale the lambda mu nu by a factor of 10, and if that coefficient is non-zero, then it's also true that the unscaled Littlewood Richardson coefficient is non-zero. Okay, so this is a sort of very, it's a sort of difficult theorem in some sense until Knudsen and Tau sort of proved this by, I'll say a little bit more about that. So let me just make a few remarks here. So it's actually a non-vanishing statement for LR coefficients. If the scaled guy doesn't vanish, the original doesn't vanish. The converse turns out to be easy. Okay, that's not a problem. But what's very, very interesting about this and what sort of leads to the significance of this is this actually related to something called Horn's conjecture and eigenvalues of 3 Hermitian matrices, some, if I have A and B Hermitian matrices with some eigenvalues, how do the eigenvalues of A plus B relate to the eigenvalues of A and B? Okay, a priori it seems to have nothing whatsoever to do with this, but it's sort of it's a long chain of interesting connections which passes through Schubert calculus and so on, which says that having this statement actually tells you something about, it proves Horn's conjecture. Okay, so very good, I'm almost done. So here's the saturation theorem that we managed to prove. So it says that the same statement, the same saturation statement also holds for the refinements that we talked about. Okay, but not for all 24 of them, or all 6 of them, depends on what your n is. We haven't managed to prove them for all of them. What we have, the following is a theorem that if the scaled refinement is a non-zero value, then the original refined guy is also non-zero. But this holds, we've been able to show it at least, provided sigma is what's called 312 or 231 avoiding is a permutation which is 312 or 231 avoiding. Okay, and this pattern avoidance is, so this, I'll briefly tell you what this means. It says, if you think of sigma as a permutation, 312 avoiding just means you cannot find 3 numbers such that the first guy is the maximum, 3, 1 and 2. So the largest guy occurs first, the smallest occurs next, and the middle guy occurs third. You cannot find a sequence of 3 numbers in the permutation which have that particular pattern of occurrence. That's what pattern avoidance means. And turns out that pattern avoidance actually stemmed from original work of Knut, Pratt and Tajan in the computer science literature. In fact, the ones they talked about what are called stack sortable numbers, I guess, or arrays. They are exactly these guys. They are exactly the 2, 3, 1 avoiding permutations. And it also comes up in other things, Stanley-Wolf conjecture, and sort of the IMSE connection here is the seminal paper of Lakshmibai and Sandhya, where they actually related a geometric property, smoothness of Schubert varieties, to something which comes from pattern avoidance. Okay, so just want to say the converse again holds for all sigma, though the forward direction we've only been able to show for this. And we in fact believe the forward implication to be true for all sigma, though we haven't found a counter example yet. Okay, and we sort of believe it's true. Okay, and sort of last 0. Okay, so just a pretty slide for the last -1 second. So which is this is sort of what goes into the proof. Thank you.